Programmers draw diagrams of data to help themselves and others understand code. If we compare the diagrams that programmers use, like this one, to how that data is shown in a print statement or a debugger, then without even knowing anything about the task, we can see a clear difference. The concrete display shows everything, while the diagram is carefully idealized, highlighting specific parts and simplifying others to show the most useful information. To be able to talk about these differences, we have developed a notion of an abstraction move, which describes an incremental shift from the concrete display to the diagram. A move consists of two parts, first selecting the appropriate data, and then either simplifying, annotating, or revisualizing it. One move here is that we have selected 3 partitions of the array and then clumped them into 3 big units. That's a simplification. Another move could have been that we selected each of those partitions and labeled them with their location on the array. That's an annotation. Let's switch diagrams to this one from the Chromium codebase. And here we can say that we have selected the entire data, which is normally shown in a hierarchy, and revisualized it with a tree layout. Based on a content analysis of 80 diagrams sourced from real-world practice, we discern different kinds of selections, revisualizations, simplifications, and annotations in these diagrams. We then translated this into Chisel, a diagramming language for JavaScript. Let's take a look at how it works. Here we have a JavaScript program that just stores an array of length n into variable L. The value of the array can be seen on the right side, and our goal is to recreate part of the diagram from earlier. Currently, the abstraction moves just display the list. Let's select it and store that selection into a variable s. A selection is indicated by a highlighted color on the diagram. Then we will revisualize it from a comma-separated value to blocks, which is how it's shown in the diagram that we want to recreate. Next, we'll partition the selection into 3s, and then clump them together. Okay, next, let's label the location of each of the selected clumps. By default, it just puts the location of each clump there, but we can specify that we want the location relative to the items in the array. This labels the literal values, and we'll now specify to label a range from 0 to n instead. In a handful of lines, we were able to get close to replicating the core qualities of this diagram. Now, the benefit of specifying the diagram through these moves, instead of just drawing it out, is threefold. First, it is data-driven. I can change the data and it updates the diagram. Here, the update is difficult to notice since all the values are clumped together. And this brings us to the second advantage, which is that I can easily switch between different moves. So for example, I can comment out the simplification and see the values. I can easily make the indices into literal values, change the number of partitions, or even change the visual layout. And lastly, I can share this script with others who may adapt it for their own tasks. Abstraction moves can capture a range of visualizations, from simple ones like this one of a graph, as well as more complicated ones involving multiple data structures and connections between them, like this syntax tree. We have been able to faithfully replicate abstractions in 78 out of the 80 diagrams from our content analysis. To conclude, we hope that this work provides a foundation for designing cognitive-friendly and customizable notations of data across debuggers and programming tools. Thank you.